Hey there, space cadets and geography gurus. Welcome to the deep dive. Before we blast off, do us a favor and hit that like button, subscribe to our channel, and tap that notification bell so you don't miss out on future cosmic expeditions.
Okay, ready for takeoff.
Today we're charting a course through the vast expanse of the universe and zooming in on our home planet Earth.
Right. From the Big Bang to the formation of planets and everything in between.
Whether you're a UPSC aspirant prepping for GS1 geography, a senior school student diving into the mysteries of Earth and space, or just a curious mind, this deep dive is your express ticket to cosmic enlightenment.
That's right. We're about to unravel the secrets of the universe, starting with that mind-blowing event that kicked it all off.
You mean the Big Bang?
Exactly.
Okay, I'm ready to have my mind blown. Tell me about the Big Bang.
All right, so picture this, a tiny, incredibly dense point packed with all the energy and matter in the universe.
Okay, got it.
About 13.7 billion years ago, this point exploded in a cosmic burst of energy and expansion. That's the Big Bang.
Wow, that's almost impossible to imagine. Everything we see today came from that single explosion.
It's amazing, isn't it? And that expansion is still happening today.
Really?
The universe is constantly growing with galaxies moving further apart.
So everything is moving away from everything else.
Well, not exactly. Here's where it gets tricky. It's the space between galaxies that's expanding, not the galaxies themselves.
I don't think I get it.
Think of it like dots on a balloon. As you inflate the balloon, the dots move apart, but they don't actually get bigger.
Ah, okay. So the space between galaxies is stretching, but the galaxies themselves stay the same size. That makes sense. So how did stars form from this expanding universe?
So the universe wasn't just a uniform soup after the Big Bang. There were tiny variations in density, and these variations acted as seeds for the formation of stars and galaxies.
So these denser regions started pulling in more and more matter, kind of like cosmic vacuum cleaners.
Exactly. These regions, called nebulae, are vast clouds of gas and dust. Gravity pulled the gas and dust together, causing these nebulae to collapse. As they collapsed, they spun faster and faster, and the material in the center got incredibly hot and dense. Eventually, the pressure and temperature at the core became so intense that nuclear fusion ignited, and boom, a star was born.
So stars are essentially giant nuclear reactors fusing atoms and releasing tremendous energy. That's fascinating.
And the light from these stars is what allows us to see them, even though they are incredibly far away.
I can imagine.
We measure these vast distances in light years, which is the distance light travels in 1 year.
Okay, time for a pop quiz. What's a light year? Don't worry, UPSC aspirants, no pressure here.
A light year is a unit of distance, not time. It's the distance light travels in 1 year, which is a whopping 9.46 trillion kilometers.
Oh.
To put that in perspective, the nearest star system to our sun, Alpha Centauri, is over 4 light years away.
Wow, that's incredibly far. So when we look at stars, we're actually seeing light that left them years, even centuries or millennia ago. It's like looking back in time.
That's a great way to think about it. And speaking of looking up at the night sky, let's talk about constellations, those patterns of stars that have helped humans navigate and tell stories for centuries.
Ah, constellations. I remember learning about Ursa Major, the big bear, and Ursa Minor, the little bear, with the North Star Polaris at the tip of its tail. I bet those were crucial for navigation in the days before GPS.
Absolutely. Sailors and travelers relied on constellations like Ursa Major to find their way, especially the North Star, which appears stationary in the sky.
How so?
That's because it's aligned with Earth's axis of rotation.
So while all the other stars seem to rotate around the North Star, it stays put, making it a reliable celestial guidepost.
Exactly. And it's not just stars up there. Our solar system is also home to a diverse cast of characters, including those rocky remnants from the early formation of planets' asteroids.
Asteroids. Those space rocks that sometimes make headlines when they come a little too close for comfort, where do they hang out?
Most asteroids reside in a belt between Mars and Jupiter, like a cosmic debris field.
Okay.
While most are relatively small, the largest asteroid series is so massive it's classified as a dwarf planet.
A dwarf planet. We'll have to talk more about those later. But first, let's talk about those shooting stars that streak across the night sky.
You mean meteors?
Yeah, those, what are they really?
Those fleeting streaks of light are meteors created when small space rocks called meteoroids enter Earth's atmosphere and burn up due to friction.
So it's not the rock itself that glows, but the air around it, superheated by the friction. It's like a cosmic light show.
Exactly. And if a meteoroid is large enough to survive its fiery plunge and hits the ground, it becomes a meteorite.
So from meteoroid to meteor to meteorite, It's all about the location and fate of these space rocks. Fascinating. Now let's turn our attention to the star of our solar system, the mighty sun.
The sun, our very own star, is a giant ball of hot gas, mostly hydrogen and helium held together by its own gravity.
Okay.
It's the engine that drives our solar system, providing us with light and warmth.
I've heard the sun described as a giant nuclear reactor. What's going on inside that fiery ball?
The sun generates its energy through a process called nuclear fusion.
Ah, yes.
In its core, hydrogen atoms are constantly fusing together to form helium, releasing tremendous amounts of energy in the process.
It's amazing how the sun can sustain this nuclear fusion for billions of years.
Yeah.
It's like a cosmic furnace that never runs out of fuel.
And the sun isn't just a passive source of energy. It's a dynamic, active star that constantly emits a stream of charged particles called solar wind.
Solar wind, it sounds like something that could blow us right off the planet.
Well, it's not quite that powerful, but it does have a significant impact on Earth.
In what way?
This continuous stream of charged particles interacts with Earth's magnetic field, creating those stunning auroras, the northern and southern lights.
Ah, the auroras. Those colorful dancing lights are a bucket list item for me. I've heard they're most visible near the poles. Why is that?
That's because Earth's magnetic field funnels these charged particles towards the poles where they interact with atoms in the upper atmosphere, causing them to glow. It's like a cosmic light show orchestrated by the sun and Earth's magnetic field.
It sounds absolutely magical.
It is.
But solar wind isn't always so benign, right? I've heard about solar flares causing disruptions on Earth.
That's right. Solar flares are sudden bursts of energy from the sun's surface, often associated with sunspots, which are cooler, darker regions on the sun's surface.
So sunspots are like blemishes on the sun's face, and solar flares are like bursts of energy from those blemishes.
That's a good analogy. While these flares create those beautiful auroras, they can also disrupt radio communications, satellite operations, and even power grids on Earth.
It's a reminder that the sun, while life-giving, can also be a bit temperamental. And speaking of the sun's behavior, you mentioned sunspots. What's the story with those?
Sunspots are fascinating features on the sun's surface. They're cooler than the surrounding areas and appear darker because they emit less light.
Why are they cooler? Is it like a cold front on the sun?
Not exactly. Sunspots are regions of intense magnetic activity. These magnetic fields suppress the flow of heat from the sun's interior, making them cooler than the surrounding areas.
So it's like a magnetic traffic jam slowing down the flow of heat.
That's a great way to put it. And the number of sunspots isn't constant. It rises and falls in a cycle of about 11 years.
A sunspot cycle. So the sun has its own rhythm, its own heartbeat. What does this cycle tell us?
The sunspot cycle helps us understand long-term variations in the sun's activity and its potential influence on Earth's climate.
Interesting.
Scientists are still studying the intricate connection between sunspots, solar flares, and their effects on our planet.
It's fascinating how the sun, even from millions of kilometers away, can influence our lives in so many ways. Now, I'm curious about those icy wanderers of the solar system comets. What are they and where do they come from?
Comets are often described as cosmic snowballs because they're made up of frozen gases, rock, and dust.
Oh, okay.
They orbit the sun in highly elliptical paths, spending most of their time in the frigid outer reaches of the solar system.
So when they get close to the sun, they heat up and create those spectacular tails, right?
Exactly. As a comet approaches the sun, the heat causes the frozen gases to vaporize, creating a glowing head called a coma and a long streaming tail that can stretch for millions of kilometers.
It's like a cosmic fireworks display. Where do these icy wanderers originate?
Many comets reside in the Kuiper Belt, a region beyond Neptune and the Oort cloud, a vast spherical shell of icy bodies even further out.
It sounds like the outer solar system is a cosmic deep freeze, teeming with these frozen relics from the early solar system.
Now, to appreciate the diversity of celestial bodies in our solar system, it's important to understand the criteria that define a planet.
Right. Back in 2006, the International Astronomical Union decided to lay down the law, so to speak, and define what makes a planet a planet. What are the rules?
There are three main criteria.
Okay, let's hear them.
First, a planet must orbit a star, which in our case is the sun. Second, it must be massive enough for its own gravity to pull it into a nearly round shape.
Makes sense.
And finally, it must have cleared its orbital path of other objects.
So a planet has to be the gravitational boss of its neighborhood, clearing out any debris in its path.
Exactly. Now let's embark on a grand tour of our solar system, starting with the smallest and closest planet to the sun, Mercury.
Mercury, the speedster of the solar system, zipping around the sun and just 88 Earth days. What's it like on this tiny world?
Mercury is a planet of extremes. It's scorching hot during the day with temperatures reaching over 400 degrees Celsius, but frigidly cold at night, dropping to negative 180 degrees Celsius. It's also a heavily cratered world bearing the scars of billions of years of bombardment.
Wow, that's quite a temperature swing. No wonder they call it a planet of extremes.
Yeah.
Next up, we have Venus, often called Earth's twin because of its similar size and mass.
Yeah.
But I have the feeling that's where the similarities end.
You're right about that. Venus is a world shrouded in thick, toxic clouds of sulfuric acid, creating a runaway greenhouse effect that traps heat and makes it the hottest planet in our solar system.
Talk about a toxic beauty. With those extreme temperatures and a poisonous atmosphere, Venus is definitely not a place for a vacation.
Now on to our home sweet home Earth, the only planet we know of that harbors life.
Earth, the pale blue dot, a cosmic oasis, teeming with life. What makes our planet so special?
Earth is unique in many ways. It has liquid water, a protective atmosphere with just the right amount of oxygen, and a stable climate that allows life to thrive.
It's amazing how all these factors came together to create the perfect conditions for life as we know it.
And let's not forget our faithful companion, the moon, tidally locked to Earth. It always shows us the same face like a cosmic dance partner.
The moon, our celestial neighbor, has captivated humans for millennia. We'll delve into the mysteries of its formation later. But first, let's continue our planetary tour. Next up is Mars, the red planet, a world that has captured our imagination for centuries.
Mars is a cold desert world, but it holds tantalizing clues that suggest it may have once been much warmer and wetter, perhaps even harboring life.
There's evidence of ancient rivers, lakes, and even oceans on Mars.
That's right.
It's incredible to think that this now barren world may have once been a vibrant, watery planet.
And Mars is a prime target for future human exploration, with missions already underway to search for signs of past or present life and to pave the way for eventual human settlement.
It's exciting to think that humans may one day walk on Mars and unravel its secrets. Now let's venture further out into the realm of gas giants, starting with Jupiter, the king of the planets.
Jupiter is a colossal world, more massive than all the other planets in our solar system combined.
Wow, it's huge.
It's a swirling mass of gas, mostly hydrogen and helium, with no solid surface.
And it's famous for that giant red spot. What is that exactly?
The Great Red Spot is a massive storm larger than Earth that has been raging on Jupiter for centuries. It's a testament to the powerful forces at play in Jupiter's turbulent atmosphere.
Wow, a storm that's been raging for centuries. It makes our earthly hurricanes seem like gentle breezes. What about Jupiter's moons? I've heard there are quite a few of them.
Jupiter has a fascinating family of over 79 known moons, including the 4 largest discovered by Galileo: Io, Europa, Ganymede, and Callisto.
Those are some pretty famous moons. What makes them so special?
Each of these moons is unique and intriguing. Io is the most volcanically active body in our solar system. Europa is thought to have a vast, salty ocean beneath its icy surface, making it a prime target in the search for extraterrestrial life.
Wow.
Ganymede is the largest moon in our solar system, even larger than the planet Mercury, and Callisto is the most heavily cratered object in the solar system.
It sounds like Jupiter and its moons are a mini solar system in themselves, full of wonders and mysteries waiting to be explored. Next up, we have Saturn, the ringed planet, a celestial showstopper.
Saturn's rings are truly a breathtaking sight. They're made up of billions of icy particles ranging in size from tiny grains to house-sized boulders, all orbiting Saturn like miniature moons.
It's amazing to think that those rings are so vast and yet so thin, less than a kilometer thick in most places.
And Saturn itself is no slouch, with a diameter nearly 10 times that of Earth and a mass nearly 100 times greater.
It's like a cosmic ballerina gracefully spinning with its dazzling rings. What about Saturn's moons? Does it have any notable ones?
Saturn has over 80 known moons, including Titan the largest, which has a dense atmosphere and lakes of liquid methane, making it a fascinating world in its own right.
A moon with lakes of liquid methane. That's mind-blowing. It seems like every time we learn something new about our solar system, it just gets more and more incredible. Now on to Uranus, the ice giant tilted on its side like a cosmic top.
Uranus's unique tilt gives it extreme seasons, with each pole experiencing 42 years of continuous sunlight followed by 42 years of darkness.
Talk about a long winter. And finally, we reach Neptune, the outermost planet in our solar system, a blue giant shrouded in mystery.
Neptune is a stormy world with supersonic winds and a fascinating moon Triton, which orbits in the opposite direction of Neptune's rotation, suggesting it may be a captured object from the Kuiper Belt.
It's a fitting end to our planetary tour, a reminder that our solar system is full of wonders yet to be explored. But before we delve into the formation of planets, let's talk about those celestial bodies that didn't quite make the cut to be classified as planets, the dwarf planets. What's the story with those?
Dwarf planets like Pluto Ceres and Eris share some characteristics with planets like orbiting the Sun and being massive enough to be round, but their gravity hasn't cleared their orbital path of other objects.
It's like the minor leagues of the planetary world, still fascinating in their own right, but not quite big enough to make it to the major leagues. Now, to understand how this diverse collection of planets and dwarf planets came to be, let's delve into the most widely accepted theory for the formation of our solar system, the nebular hypothesis.
The nebular hypothesis proposes that our solar system formed from a giant rotating cloud of gas and dust called a solar nebula.
Okay, let's rewind the cosmic clock billions of years to the birth of our solar system. Imagine this vast cloud of gas and dust swirling through space. What happened next?
Under the influence of gravity, this nebula began to collapse in on itself like a cosmic pancake batter being poured onto a hot griddle.
And as it collapsed, it started to spin faster and faster,
Mhm.
like a figure skater pulling in their arms.
Exactly. This spinning motion caused the cloud to flatten into a rotating disk, with most of the material concentrated in the center where the sun would eventually ignite.
So it's like a cosmic pizza dough being tossed and spun, creating a thin crust with a bulge in the middle.
Within this swirling disk of gas and dust, tiny particles began to clump together due to electrostatic forces like cosmic dust bunnies forming under your bed.
And as these clumps grew larger, their gravity attracted more and more material, eventually forming planetesimals, the building blocks of planets.
That's right. In the inner solar system where it was hotter, only rocky materials could condense, giving rise to the terrestrial planets, Mercury, Venus, Earth, and Mars.
But in the outer solar system, where it was much colder, gases like hydrogen and helium could condense, forming the gas giants, Jupiter, Saturn, Uranus, and Neptune.
Exactly. And the leftover debris from this planet-forming process ended up in regions like the asteroid belt, Kuiper belt, and Oort cloud, a cosmic graveyard of sorts.
It's amazing how this chaotic dance of gravity, matter, and temperature sculpted the solar system we know today.
Now, while the nebular hypothesis is widely accepted, there are alternative theories, like binary theories, which suggest that our sun might have had a companion star in its early days.
So it's like a cosmic buddy system with two stars dancing around each other, influencing the formation of planets. What do those theories suggest?
These binary theories offer intriguing alternative perspectives on how our solar system might have formed, but they haven't garnered as much support as the nebular hypothesis.
It's a reminder that there's always more to learn, and that our understanding of the universe is constantly evolving. Now let's shift our focus to the evolution of our own planet Earth from a barren rock to the vibrant biosphere we know and love today.
Earth's early days were anything but hospitable. Imagine a molten, fiery world with a thin, toxic atmosphere bombarded by asteroids and comets. It's hard to believe that this hellish landscape would eventually give rise to life.
So how did Earth transform from a fiery inferno into a life-sustaining paradise? What were the key stages in this remarkable evolution?
It's a story of gradual cooling, differentiation, and the emergence of key features like the lithosphere, hydrosphere, and atmosphere.
Okay, let's break down these big words. What exactly is the lithosphere?
The lithosphere is the solid, rocky outer layer of Earth, encompassing the crust and the uppermost part of the mantle. Think of it as Earth's skin.
So how did this rocky skin form from the molten chaos of early Earth?
As Earth gradually cooled, heavier elements like iron sank towards the center, forming the core, while lighter elements rose to the surface.
It's like a giant cosmic sorting machine, separating materials based on their density.
Exactly. This process of differentiation led to the formation of a layered structure with a dense core, a molten mantle, and a solid crust, which eventually cooled and solidified to form the lithosphere.
So the Earth's crust is like the cooled and hardened shell of a cosmic egg. Now let's talk about the hydrosphere, the realm of water. How did Earth get its oceans?
As the molten Earth cooled, water vapor trapped in the interior was released through volcanic outgassing.
It's like the Earth was sweating out its oceans.
And as the planet continued to cool, this water vapor condensed in the atmosphere and fell as torrential rain, filling the vast depressions on Earth's surface to form the oceans.
So it was a cosmic downpour of epic proportions.
Yeah.
Now let's move on to the atmosphere, the gaseous envelope that surrounds our planet.
Right.
We breathe air, which is part of the atmosphere, so its evolution is crucial to our existence.
The early atmosphere was very different from what we breathe today. It was primarily composed of hydrogen and helium, similar to the sun's composition.
So our early atmosphere is like a mini-sun.
In a way, yes. But this primordial atmosphere was eventually stripped away by the intense solar winds from the young sun.
So the sun was a bit of a bully in its early days, blowing away our first atmosphere. What happened next?
The second atmosphere was formed by volcanic outgassing, releasing gases like water vapor, carbon dioxide, nitrogen, and sulfur dioxide from Earth's interior.
So it's like the Earth was exhaling its new atmosphere.
The second atmosphere was still quite hostile to life as we know it, but it set the stage for a dramatic transformation.
And what caused this transformation?
The emergence of life itself, specifically the evolution of photosynthetic organisms like cyanobacteria, which began to release oxygen as a byproduct of their metabolism.
So life itself terraformed our planet, transforming a toxic atmosphere into the oxygen-rich air we breathe today. It's amazing how life played such a crucial role in shaping our planet.
And this transformation from a primordial atmosphere to an oxygen-rich environment paved the way for the evolution of more complex life forms.
It's a remarkable story of coevolution, with life and the planet shaping each other over billions of years. Now, before we dive into the theories of moon formation, let's talk about the geologic timescale, a sort of calendar for Earth's history. What exactly is the geologic timescale?
The geologic timescale divides Earth's history into a hierarchy of time intervals. Eons, eras, periods, epochs, and ages. It's a framework that helps us understand the sequence of events that shaped our planet and the evolution of life.
Okay, let's start with the biggest chunks of time, the eons. What are the major eons in Earth's history?
Earth's history is characterized by 4 eons, from oldest to youngest: the Hadean, the Archean, the Proterozoic, and the Phanerozoic. For UPSC aspirants, this is crucial information.
So it's like dividing Earth's history into 4 chapters, each representing a major phase of development. Let's start with the first chapter, the Hadean Eon. What happened during this eon?
The Hadean Eon represents Earth's early days, a time of intense heat, volcanic activity, and frequent bombardment from space. It's named after Hades, the Greek god of the underworld, which is quite fitting given the hellish conditions on early Earth.
It sounds like a pretty rough time to be around. What about the Archean Eon?
The Archean Eon marks the emergence of the first life forms, simple, single-celled organisms, and the beginning of continental formation. It's a time of significant change, with the Earth starting to cool down and stabilize.
So life emerged from the primordial soup of the Archean Eon. That's incredible. What about the Proterozoic Eon?
The Proterozoic Eon is a time of dramatic transformations, with the rise of oxygen in the atmosphere thanks to photosynthetic bacteria, and the emergence of more complex life forms, including eukaryotes, cells with a nucleus. This eon sets the stage for the explosion of life in the next eon.
So the stage is set for the evolution of more complex life forms. And finally, we arrive at the Phanerozoic Eon, the current eon in which we live. What makes this eon so special?
The Phanerozoic Eon, which spans from 541 million years ago to the present, is characterized by the diversification of complex life, the formation and breakup of supercontinents like Pangaea, and the evolution of the familiar landscapes we see today. It's divided into 3 eras: the Paleozoic, the Mesozoic, and the Cenozoic. The Phanerozoic is like the grand finale of Earth's history, showcasing the incredible diversity and complexity of life that has evolved over billions of years.
That's a lot to unpack, but it's fascinating to see how Earth has evolved through these distinct eons, each with its own unique characteristics and milestones. Now let's shift gears a bit and talk about how we navigate our planet and understand its various regions. I'm talking about latitude and longitude, the coordinates that define our location on Earth. Can you explain these concepts?
Absolutely. Latitude and longitude are like the address system of our planet, allowing us to pinpoint any location on Earth's surface. This is a fundamental concept in geography and is often asked in UPSC prelims and mains exams.
Okay, let's start with latitude. How does latitude work?
Latitude tells you how far north or south you are from the equator, the imaginary line that circles Earth at 0 degrees latitude, dividing it into the northern and southern hemispheres. Latitude lines, also known as parallels, run east-west and are parallel to each other.
So the equator is like the waistline of Earth, and latitude lines are like belts cinched around the planet at different distances from the equator.
Exactly. The North Pole is at 90 degrees north latitude, and the South Pole is at 90 degrees south latitude.
Now, what about longitude?
Longitude lines, also known as meridians, run north-south and converge at the poles. They measure how far east or west you are from the prime meridian, an imaginary line that runs through Greenwich, England at 0 degrees longitude.
So the prime meridian is like the center line of Earth, dividing it into the eastern and western hemispheres. And longitude lines are like